Everybody, in this video lecture I am going to discuss about directions and planes in crystals and Miller indices. In order to study a crystal structure, it is important to understand the concepts of directions and planes in a crystal. Depending upon the unit cell of a particular crystal structure, the arrangement of atoms in different directions and planes vary. A thorough study of the crystal structure will lead to a complete understanding of the arrangement of atoms, the neighboring atoms of a particular atom, and the interatomic distances between various atoms in the crystal. All the physical and chemical properties of a solid could therefore be well explained depending on the crystal structure. Miller indexing is actually a system of indexing, that is, identifying and marking planes in a crystal structure with a set of integer numbers enclosed in parentheses. These planes contain atoms, and different planes contain not only different concentration of atoms but also their arrangement is different. Before we begin to study Miller indices, we shall start by understanding crystal directions and how to identify and differentiate between different directions in a crystal. First, let us start with a simple two-dimensional lattice, and then we can extend the same concepts to a real 3D lattice that a crystal is. Shown here on the left is a two-dimensional crystal lattice, specifically a square lattice, in which two arbitrary directions are represented by two lines. The first line is shown in black, whereas the next one is in blue. The first line has been labeled or indexed as 1, 1. That means the direction of the first line in this 2D lattice is 1, 1. Whereas the second line is labeled as 3, 1. Now, the smallest possible values of x and y through which this line passes is 1, 1. That is, 1 unit along the x direction and 1 unit along the y direction. That is this point. So, through which this line is passing, and hence the direction is 1, 1. Now, the blue line, the smallest possible value along the x direction is 3 units, and the smallest possible integer value along the y axis is 1 unit. So, this line, the direction of this line is 3, 1. Now, if you see this line along the x axis, first unit cell it cuts at 1/3 of the y axis, next unit cell it cuts at 2/3, and in the next unit cell it completely goes through 3, 1, the point 3. Therefore, 3 units it took for the line along the x axis and 1 unit it took along the y axis to get the smallest possible values for x and y, smallest possible integers for x and y. Now, we will extend the same idea to the 3-dimensional lattice shown here, which is a more real lattice. Here, several directions are shown. For example, OA, OB, OC, OD, and OE. 5 different directions are shown in this crystal lattice. It is a cubic lattice. Let us first try to identify the direction OA. Now, this line is on the x y plane, and therefore it has only valid coordinates for x and y directions, both being 1 unit along the x direction and 1 along the y direction. So, this direction can be indexed as 1, 1 and 0. So, 1, 1, 0 enclosed in a square parenthesis or square brackets is called the direction of this line OA. Similarly, if you try for OB, it is going through a point here which is half unit along the z direction and 1 unit along the x direction, but half is not an integer. So, we have to actually assume the extension of this line, and that would cross 2 units on the x direction and 1 unit on the z direction and no unit on the y direction, that is it is lying on the x z plane. Therefore, the indexing for this line OB is 2 on the x. So, 2 no unit, no intercept or no does not pass through any point on the y direction. So, it is 0 and 1 unit on the z by the time it crosses 2 here. So, 2 0 1, this is for OP. OC, if you do the same logic, it is cutting here at half of z, which is not an integer. So, to make it an integer, this line has to be twice. So, basically OC is going to be 0 0 2. OD, extending the same logic, is cutting at half the z direction. If you extend this beyond this point from here to here, you would see that it is spanning 2 units along the y direction, and it is on the yz plane. Therefore, 0 along the x, 2 along the y and 1 along the z. So, 0 to 1 is the direction for this line OD. OE, on the other hand, is passing through the point 1 1 1, 1 unit along the x, 1 along the y and 1 along the z. So, it is 1 1 1 enclosed in a square bracket. Now, this is how we can identify different directions in a 3-dimensional crystal lattice. Now, we will move on to identification of different planes in a crystal lattice, and this system of identification was devised by Miller, and therefore, this is called Miller indexing. That is, Miller devised a method to designate, identify, distinguish one set of planes from another in a crystal lattice. This is called Miller indexing of the lattice planes. Now, there are a few steps, simple steps involved in identifying different planes in a crystal, and these are the 4 steps given here. You can clearly see that the first step is the coordinates of the intercepts made by the plane along the 3 crystallographic axes x1, x, y and z. That is, you have to arbitrarily choose a set of 3 coordinate axes for the given unit cell. The given unit cell may be a cubic cell. See, here in this case we have taken a cubic unit cell, in which the coordinate axes conventionally are taken to be along the edges of the cube, any set of 3 edges of the cube. Generally, the bottommost left corner is taken as the origin of the coordinate axis system, with x positive x pointing out of the page, positive y to the right of the origin and positive z above the origin. This is how conventionally it is followed. By following the same convention, one can choose the origin, and in cases where the origin has to be shifted also, one can do by shifting the origin either from this point to this point or the other any of the nearest corners of the cube. Right, as we move along, we will understand this in a better way. Now, the second step involves the intercepts being expressed as multiples of the unit cell dimensions or lattice parameters along the 3 axes. Now, this is a given plane will intercept each of the 3 axes generally at different points. These are called the intercepts of the plane along the 3 crystallographic axes, and these intercepts have to be written in terms of the lattice parameters A, B and C of the unit cell. That is, 1 unit here which is A, 1 unit is B here and 1 unit is C along the x, y and z direction, forming the unit cell of the crystal lattice. Now, then the reciprocals of these numbers are taken, If the reciprocals are not whole numbers or integers, then we have to reduce it to smallest set of integers and put them in a set of parentheses, and this notation is the Miller indexing or index of the given set of parallel planes. Now, there are parallel planes for a given lattice I have drawn here. For example, for the same lattice I have vertical planes, horizontal planes, diagonal planes, two sets of diagonal planes. Now, each set of planes, like 3 planes, vertical planes are there, has one Miller index, one number, one set of 3 numbers put in parentheses. Similarly, for these horizontal planes as well as these diagonal planes. So, they are all parallel, so their Miller index is same. Right. Now, we can discuss this in more detail. Whatever steps are involved, I have explained this in a more detailed fashion here. Along the x, y and z directions, let us say a given plane makes intercepts 2 times on the x direction, 3 times the lattice parameter on the y direction and 1 time along the z direction. Then the intercepts are 2a, 3b and c. That is, the coordinates are of the intercepts are represented in terms of the lattice parameters a, b and c. Now, the integer numbers are collected or extracted. In this case, it is 2, 3 and 1. So, it is denoted in terms of alphabets p, q and r. So, p is equal to 2, q is equal to 3 and r is equal to 1. Now, if you express these intercepts as multiples of unit cell dimensions, that is nothing but the numbers 2, 3 and 1 respectively. Now, if you take reciprocals of these 3 intercepts, you will have 1 by 2, 1 by 3 and 1 or 1 by 1. Now, if you want to reduce it to the lowest common multiplier by multiplying it with the lowest common multiplier, which is happens to be 6 in this case, you will have 6 into half 3, 6 1/3 are 2, 6 1s are 1. So, 3, 2, 6 happens to be the Miller index of the given plane. As I already mentioned, the choice of origin is arbitrary. So, a convention can be followed for consistency, but generally when a given plane does not pass through a particular set of axes, then the origin can be shifted so that the plane intercepts all the 3 axes. So, generally one has to try to shift the origin in such a way that each of the 3 axes are intercepted by the plane to be identified. That is the general logic. Now, we will work out a few planes here to understand the concept of Miller indices in a better way. Now, these examples will really help us to get better clarity on the concept of Miller indices. First, let us go to this plane which is shaded in gray color. Now, if the origin is taken to be at this point, then this is x direction, this is y direction and this is z direction. Now, this plane is making an intercept only along the z direction and not along the x or y direction. So, it is parallel to the x as well as y directions, but cutting the x axis at 1 unit. So, the Miller index would be straight away 0, 0, 1, 0 along the x, 0 along the y, because it is intercepting the x axis and y axis at infinity. The reciprocal of infinity is 1 by infinity is 0. So, you will have Miller index of 0 for the x, 0 for the y and 1 by 1 is 1. So, 1 for the z direction. So, 0, 0, 1 enclosed in parentheses is the Miller index for this particular plane that is mentioned here in this next slide. Right, going back for the next plane, this is intercepting the y axis at 1 units, but it is parallel to the z as well as the x. So, it is 0, 1, 0. The third one is interesting. the origin is here, the plane is actually on the origin, and this is x, this is z, and this is y. Now we have to shift to see where it is actually intercepting the any of the three axes. Straight away, if you shift the origin to this point, let us say, then you would think that now this is the y direction, this is the z, and the x is now this way. That means this plane is intercepting the negative x axis at 1 unit, right. That means the coordinate for this is -1, which is generally represented as bar 1. It is parallel to both the y as well as the z directions, because z is here and y direction is here. The plane is parallel to both this thing. So it is 0, 0. So the third plane is 1 bar 0, 0. This is 1 bar 0, 0. In the same way, if you try to identify this plane has origin, let us say here, origin of the coordinate system is here, and this is x axis, the plane is parallel to the x axis. So straight away x coordinate should be 0. It is intercepting the y axis at 1 unit, so 1. It is intercepting the z axis at 1 unit exactly, so it is 1, 0, 1, 1. You can check it, 0, 1, 1. This plane is passing through the origin again, so you need to shift the origin to this point. Now this is your z, this is your negative x, and this is your y. So it is cutting or intercepting the negative x, so it is 1 bar, positive y 1, and parallel to the z, so 0, 1 bar 1, 0, 1 bar 1, 0. Right. Next is, again it requires an origin shift from this point to this point, so that all the three axes are cut, or at least 2 of them are cut. So this is x, it is cutting at -1, it is cutting z at 1, it is not intercepting the y at all. So it is 1 bar 0, 1. You can go and check here, 1 bar 0, 1. Right. In the same way, we can proceed to identify the last 3 set of planes in the slide, and that is the bottommost row of 3 planes. For clarity, I am just rubbing off the old things. Yeah, here you can see that if you shift the origin, because the plane is passing through the origin, ideally you should be trying to shift it to this point. If you shift this point, it is intercepting the y at 1, x at 1, and z at 1, but x is -1. So it is 1 bar 1, 1. Okay. Now this plane, if you try to do this, this is cutting it at 1, 1, and 1. So it is straight away 1, 1, and 1. The other plane that is represented here is just a parallel plane, so it also has the same index. Similarly, 2 parallel planes are represented here, and one can index any one of them to understand this. Now, if this is the origin, this plane is passing through the origin, so we can shift the origin to this new point. Now, this is negative z, this is positive y, this is positive x. So, the coordinate system is now like this, with origin here. The plane is like this. So, the plane is intercepting z axis at -1. So, last z coordinate is 1 bar, it is cutting x at 1 and y at 1. So, 1 1 1 bar is the indexing for this plane. You just verify here 1 1 1 bar. So, this way one can index all the planes very easily by using this kind of a method. Right, let us do some more planes for better practice. Now, there is an atom at the body center of the unit cell here, that is represented in red color. So, one can understand these planes are diagonal planes, basically body diagonal planes. The first three here represented are all are in fact body diagonal planes, all the 6 planes that are to be identified in this case. Now, the unit cell has been slightly kind of rotated in comparison with the previous this thing. So, the origin still can be taken there wherever we originally assumed, and then try to kind of work this out. Suppose if the origin is at the bottom left corner of the unit cell, then this plane is actually passing through that. So, what one can actually do is one can shift the origin, let us say to this point. From here to here you are shifting. Now, if you shift this here, this is negative z, this is negative x, this is positive y. So, this plane should be cutting it at positive y, and this plane is parallel to the x axis. So, it is 0 1 1 bar, 0 1 and 1 bar. Right. Then this one here is, if the origin is appropriately shifted to let us say this point, then this is positive x 1 unit, positive y, positive z 1 unit, this direction, positive y and negative x parallel. So, it is 0 1 1 0 1 1 plane. Similarly, if you do this plane, you have to probably shift the origin to a suitable point, because this is kind of going parallel to the y direction, plane is parallel to the y direction, and if you shift the origin let us say to this point, because then your z will be like this, your x is like this. So, it is parallel to y, and axis direction is unchanged. So, it is 1, and it is parallel to the y direction anyway. So, it is 0 and it is cutting y. So, it is 1 0 1 0 1. In the same way, if you do the next 3 planes, please work it out. I am not going to completely explain this now. It is 1 bar 0 1 for this plane, it is 1 1 0 for this plane, and it is 1 bar 1 0 for the last plane. Therefore, the different set of planes can be identified following this way. So, this is how different planes in a given crystal lattice can be indexed. In the same way, planes of other systems such as orthorhombic, tetragonal or monoclinic etc. can be easily indexed using Meller indexing.